To set the taps on a 480-volt transformer, you need to follow a specific procedure to ensure optimal performance and avoid overloading the transformer. The first step is to determine the full load current. You can calculate the full load current of the transformer using the formula full load current equals power in kVA divided by voltage in volts. This calculation is crucial for selecting the correct tap setting. Most 480-volt transformers have taps at 512 volts, 528 volts, and 544 volts. The tap setting you use depends on the full load current. If the full load current is less than 65%, which indicates a low load condition, the 512-volt tap is typically selected. If the full load current is between 65% and 100%, which indicates a normal load, the 480-volt tap is appropriate. If the full load current is greater than 100%, which indicates an overloaded transformer, the 528-volt or 544-volt tap should be used. After determining the appropriate tap setting based on the full load current, the next step is to physically set the taps. This should always be done with the transformer energized to ensure safety. Open the tap changer compartment and locate the tap changer handle or dial. Turn the handle or dial to the desired tap setting, making sure it is correctly engaged to avoid any issues with the connection. Once the taps are set, energize the transformer. Then measure the secondary voltage at the transformer terminals to verify that it is within the desired range. Adjust the tap setting slightly if necessary to achieve the desired voltage. It is important to note that the secondary voltage should be set to 480 volts plus 10% at full load to compensate for voltage drop in the distribution system. The 512-volt tap is generally not recommended for full load operation because it can cause transformer overloading due to a higher current draw. If the transformer is overloaded, meaning the full load current is greater than 100%, the secondary voltage will be higher than normal, and the 528-volt or 544-volt tap should be used to correct this. To elaborate further, the selection of the correct tap is essential for efficient transformer operation and longevity. Operating a transformer at the wrong tap setting can lead to various problems, including reduced efficiency, increased losses, and premature failure. Firstly, if the tap setting is too high for the load, the secondary voltage will be higher than necessary, leading to increased energy consumption and potential damage to connected equipment. Secondly, if the tap setting is too low for the load, the secondary voltage will be lower than necessary, which can cause equipment to malfunction or operate inefficiently. Thirdly, operating a transformer at an overloaded condition for an extended period can significantly reduce its lifespan. The excessive heat generated by the overload can degrade the insulation and other components, leading to premature failure. Therefore, it is important to monitor the full load current and adjust the tap settings accordingly to ensure that the transformer is operating within its rated capacity. Additionally, regular maintenance and inspection of the transformer are essential for identifying potential problems early on. This includes checking the tap changer mechanism for any signs of wear or damage, inspecting the connections for loose or corroded terminals, and monitoring the transformer's temperature to ensure that it is within the acceptable range. Furthermore, it's crucial to understand the role of voltage drop in electrical distribution systems. Voltage drop is the reduction in voltage that occurs as electrical current flows through the conductors from the source to the load. This voltage drop is caused by the impedance of the conductors, which includes both resistance and reactance. The amount of voltage drop depends on several factors, including the length of the conductors, the size of the conductors, the current flowing through the conductors, and the power factor of the load. In order to compensate for voltage drop, it is common practice to set the secondary voltage of the transformer slightly higher than the nominal voltage of the load. This ensures that the voltage at the load remains within the acceptable range, even under full load conditions. The 10% voltage boost at full load that was mentioned earlier is a typical value used to compensate for voltage drop in many distribution systems. However, the actual amount of voltage boost required may vary depending on the specific characteristics of the system. The selection of the appropriate transformer tap is not just a one-time task. It's important to periodically review the tap setting based on changes in the load or the distribution system. For example, if new loads are added to the system, the full load current of the transformer may increase, requiring a different tap setting. Similarly, if the distribution system is modified, the voltage drop may change, requiring an adjustment to the transformer tap. In addition to calculating the full load current, it's also helpful to monitor the transformer's operating temperature. Transformers generate heat as a result of core losses and winding losses. The amount of heat generated depends on the load, the voltage, and the efficiency of the transformer. Excessive heat can damage the transformer's insulation and other components, leading to premature failure. Therefore, it is important to ensure that the transformer is properly ventilated and that the operating temperature is within the acceptable range. Temperature monitoring can be done using temperature sensors or thermal imaging cameras. These tools can help identify hotspots and other areas of concern. It's also important to consider the impact of harmonics on transformer performance. Harmonics are distortions in voltage and current waveforms that can be caused by nonlinear loads such as electronic devices and variable speed drives. Harmonics can increase the transformer's losses, reduce its efficiency, and cause overheating. In order to mitigate the effects of harmonics, it may be necessary to install harmonic filters or use a transformer that is specifically designed to withstand harmonic currents. Finally, it is crucial to follow all applicable safety procedures when working with transformers. Transformers operate at high voltages and can be dangerous if not handled properly. Always de-energize the transformer before performing any maintenance or adjustments. Use appropriate personal protective equipment such as gloves and safety glasses. And be sure to follow all applicable electrical codes and standards. Transformers play a critical role in electrical power distribution systems, and understanding how to properly set the taps is essential for ensuring their safe and efficient operation. Now let's delve a bit deeper into the intricacies of each step in the transformer tap setting procedure. Regarding step 1, determining the full load current involves more than just applying the formula. It requires a thorough understanding of the load characteristics connected to the transformer. The load may consist of various types of equipment, each with its own power requirements and operating cycles. Therefore, it's important to consider the diversity factor and the load factor when calculating the full load current. The diversity factor is the ratio of the sum of the individual maximum demands of the loads to the maximum demand of the entire group of loads. It accounts for the fact that not all loads will be operating at their maximum demand simultaneously. The load factor is the ratio of the average load over a period of time to the peak load during the same period. It reflects the utilization of the transformer over time. A higher load factor indicates that the transformer is being used more efficiently. In practice, determining the full load current may involve using historical data, load monitoring equipment, or engineering calculations. It's important to use accurate and reliable data to ensure that the tap setting is appropriate for the actual load conditions. Moving on to step 2, selecting the tap setting involves considering the available tap positions and their corresponding voltage ratios. The tap positions are typically expressed as a percentage of the nominal voltage. For example, a plus or minus 5% tap means that the voltage can be adjusted by plus or minus 5% of the nominal voltage. The voltage ratio is the ratio of the primary voltage to the secondary voltage. It determines the amount of voltage transformation provided by the transformer. The tap settings are chosen to compensate for voltage variations in the supply voltage and voltage drop in the distribution system. The goal is to maintain a stable and acceptable voltage at the load terminals. The selection of the tap setting may also involve considering the impedance of the transformer. The impedance is a measure of the transformer's opposition to the flow of alternating current. It affects the voltage regulation of the transformer, which is the change in secondary voltage from no load to full load conditions. A transformer with a higher impedance will have a larger voltage drop under load. Now let's address the actual physical adjustment in step 3. Setting the taps requires careful attention to detail and adherence to safety procedures. The tap changer mechanism is typically located inside the transformer enclosure and may be either a manual or an automatic type. Manual tap changers require the operator to physically move the tap selector switch to the desired position. Automatic tap changers use a control system to automatically adjust the tap position based on the load conditions. Before setting the taps, it's important to energize the transformer and isolate it from the power source. This is to prevent electrical shock and other hazards. The tap selector switch should be inspected for any signs of wear or damage before being operated. The switch should be moved smoothly and deliberately to the desired position, ensuring that it is fully engaged and locked in place. After setting the taps, it's important to verify the tap position using a multimeter or other measuring device. This is to ensure that the taps have been set correctly and that the transformer is operating at the desired voltage ratio. Finally, in step 4, adjusting the secondary voltage involves monitoring the voltage at the load terminals and making adjustments to the tap setting as needed. The voltage should be measured under both no load and full load conditions to determine the voltage regulation of the transformer. If the voltage is too high or too low, the tap setting should be adjusted accordingly. The adjustment should be made in small increments to avoid overshooting the desired voltage. It's also important to consider the impact of the tap setting on the transformer's efficiency. Each tap setting has a slightly different efficiency characteristic. The tap setting that provides the best voltage regulation may not necessarily be the most efficient setting. Therefore, it's important to consider both voltage regulation and efficiency when selecting the tap setting. And to expand further still, understanding the types of transformers and their specific tap configurations is very important. There are primarily two types of transformers: step-up transformers and step-down transformers. Step-up transformers increase the voltage from the primary side to the secondary side, while step-down transformers decrease the voltage. In the context of the initial question, a 480-volt transformer is typically a step-down transformer, reducing a higher voltage to 480 volts for industrial or commercial use. The tap configurations vary among manufacturers and transformer designs. Some transformers have taps only on the primary winding, while others have taps on both the primary and secondary windings. The taps allow for adjustments to the turns ratio of the transformer, which directly affects the output voltage. For example, if a transformer has a primary voltage of 4,800 volts and a secondary voltage of 480 volts, the turns ratio is 10:1. If a tap is set to increase the primary voltage by 5%, the new primary voltage would be 5,040 volts. This would result in a slightly higher secondary voltage as well, maintaining the 10:1 turns ratio. In practice, selecting the correct tap involves a combination of calculation, measurement, and experience. It's important to understand the load characteristics, the distribution system, and the transformer specifications to make an informed decision. Remember, it's better to err on the side of caution and consult with a qualified electrician or engineer if you're unsure about the correct tap setting. We can also touch on the role of power quality and its influence on transformer tap selection. Power quality refers to the characteristics of the electrical power supply, including voltage stability, frequency stability, and harmonic content. Poor power quality can affect the performance and lifespan of transformers and other electrical equipment. Voltage sags, swells, and transients can cause equipment to malfunction or fail. Harmonics can increase transformer losses and cause overheating. Therefore, it's important to monitor power quality and take steps to mitigate any problems. If the power quality is poor, it may be necessary to adjust the transformer taps to compensate for voltage variations or harmonic distortion. For example, if the supply voltage is consistently low, it may be necessary to raise the tap setting to boost the secondary voltage. If the supply voltage is consistently high, it may be necessary to lower the tap setting to reduce the secondary voltage. In some cases, it may be necessary to install power quality improvement equipment such as voltage regulators or harmonic filters to address the underlying problems. Voltage regulators can maintain a stable voltage supply despite variations in the load or the supply voltage. Harmonic filters can reduce the harmonic content of the electrical power, improving the performance and lifespan of transformers and other equipment. Let's explore some practical scenarios where transformer tap adjustments are necessary. Consider a manufacturing plant that has recently added a new production line. The new production line requires a significant amount of electrical power, increasing the load on the existing transformer. As a result, the voltage at the end of the distribution system drops below the acceptable level. In this scenario, it may be necessary to adjust the transformer taps to boost the secondary voltage and compensate for the increased voltage drop. The tap setting would be raised to increase the turns ratio and provide a higher secondary voltage. Another scenario involves a commercial building that experiences frequent voltage sags due to problems with the utility grid. The voltage sags cause sensitive electronic equipment to malfunction, disrupting business operations. In this case, it may be necessary to install a voltage regulator to maintain a stable voltage supply. The voltage regulator would automatically compensate for the voltage sags, ensuring that the equipment receives a consistent and reliable power supply. These examples highlight the importance of understanding the load characteristics and the distribution system when selecting transformer taps. It's not just a matter of calculating the full load current and choosing the corresponding tap setting. It's also important to consider the voltage regulation, the power quality, and the potential for future changes in the load or the distribution system. It is important to also talk about the documentation and record keeping of any tap adjustments. Whenever transformer tap settings are adjusted, detailed records should be maintained. This documentation should include the date of the adjustment, the reason for the adjustment, the initial tap setting, the final tap setting, and any measurements or calculations that were performed. The record should be kept in a safe and accessible location for future reference. This documentation is important for several reasons. Firstly, it provides a history of the transformer's tap settings, which can be helpful for troubleshooting problems or making future adjustments. Secondly, it demonstrates that the tap settings have been made in accordance with established procedures and best practices. Thirdly, it provides a basis for evaluating the performance of the transformer and identifying potential areas for improvement. In addition to maintaining records of tap adjustments, it's also important to keep other relevant documentation such as the transformer's nameplate data, the manufacturer's instructions, and any engineering studies or calculations that have been performed. This documentation can be invaluable for understanding the transformer's capabilities and limitations and for making informed decisions about its operation and maintenance. We can also talk about the training and qualifications that personnel should have before adjusting taps. Adjusting transformer taps is a task that should only be performed by qualified and trained personnel. These personnel should have a thorough understanding of electrical theory, transformer operation, and safety procedures. They should also be familiar with the specific type of transformer being adjusted and the applicable codes and standards. The training should include both classroom instruction and hands-on experience. The classroom instruction should cover topics such as transformer principles, tap changer operation, voltage regulation, power quality, and safety procedures. The hands-on experience should involve working with actual transformers under the supervision of experienced personnel. The training should also include instruction on the use of measuring instruments, such as multimeters and power quality analyzers. These instruments are essential for verifying the tap settings and monitoring the transformer's performance. In addition to formal training, it's also important for personnel to stay up to date on the latest developments in transformer technology and best practices. This can be achieved by attending industry conferences, reading technical publications, and participating in continuing education programs. It is also important to consult with a transformer manufacturer or a qualified electrical engineer if you have any questions or concerns about adjusting transformer taps. They can provide valuable guidance and support to ensure that the task is performed safely and correctly.